Welcome back to NE 630, nuclear reactor analysis or nuclear reactor theory. So just to give you a bit of information about the midterm examination before we hand in the exam by the end of this week or early next week. So the exam will be composed of 6 problems, hopefully 5 to 6 problems. One problem will be just definitions, 5 definitions. So you just look at the definitions inside the book, and nothing in the exam will be outside what you guys took in the class. So if you review the material that you got in the class and online, you will be able to solve the exam. The second problem will be from chapter number 1 regarding the nuclear physics definitions and stuff like this. Problem number 3, I think, will be regarding definitions of multiplication factors and changes of multiplication factors when you change, let's say, a moderator or whatever. Problem number 4, I don't remember the problem number 4, yeah, problem number 4, but I think problem number 5 or 6, I don't remember, is a spherical geometry, so solution of the diffusion equation in a spherical geometry. So if you just figure out how to solve it, and again, as I just stated, I will not accept spitting the formula for the flux and say, oh, this is the flux, so the solution is so and so. You have to show me the steps, how did you calculate the flux? Because this is a mathematical course, and it is a training for your mathematical expertise. So if you do not know how to do it, the course is not useful for you. So let's now move to the new chapter number 4. So as I just stated several times about how nuclear reactors are being designed, for example, we stated that you have to solve, just in the case of this, in the sake of this, let's say, course, we are using the diffusion equation. Nobody will solve a single velocity or mono energetic velocity or whatever, let's say, a single speed diffusion equation. Usually people will solve, if you want to solve the diffusion equation in the course, you will solve what they call multi-group diffusion equation. And this is a good approximation, for example. So to solve the multi-group diffusion equation, you have to do what? You have to solve the diffusion equation, but in groups instead now of a single velocity. When we derive the diffusion equation, we said that, okay, we have a single speed, so we average the flux, average the sigmas and d and nu over the energy or the flux distribution. Where we got the flux? So we have to solve the diffusion equation to get the flux. So how did we get the flux to average over the values for, let's say, sigma absorption, sigma fission, nu, and d? So those are called weighting flux, and the weighting flux is just by studying the neutron distribution in the nuclear reactor, we will be able to get a weighting flux. So that we will take those weighting flux, plug them in the formulas for the averaging, whether you average over one speed or you average in a group of energy. Let's say between E and E plus delta E, we will call it, this is group number I. So let's assume that in multi-group diffusion equation, this is the fission, E fission, and let's say the 0 is here, and this is 1 electron volt, which is the energy, cutoff energy for thermal. And let's assume that you get an energy between E, let's say E and E plus delta E, and we'll call it G. So we'll call this group G. Then when you write your diffusion equation now will be 1 over Vg, which is the velocity in group G, d by dt for the flux in group G, equal to d, which is the diffusion coefficient in group G, multiplied by nabla square phi in group G. Then you will have negative sigma absorption in group G multiplied by the flux in group G, plus nu sigma fission in group G multiplied by the flux in group G. But is it like this? No, we have to take into consideration, like, okay, if group G is here, so this is EG, and this is EG plus delta EG. So this is the thickness here is delta EG. So maybe there is another group I, we'll call it EI, and EI plus delta I. So there is another group, and the scattering in this group, sigma scattering, at energy EI, and will go to energy EG. So what's this? This is called out of group scattering cross section, and this is just sigma scattering at energy EI multiplied by the probability that if you have initial energy in I, you will go to the final energy in G. So this is this. So the total number of interaction inside the group here will be just sigma scattering. Will be just sigma scattering of EI, and you go to EG multiplied by the flux at the group I, but you have to sum over all the groups I from I equal to 1 or here up to the, let's say, up to the energy, whatever, energy EI or whatever. So this is called all the sources that will come as a result from the scattering from those groups. Yes? So you will have a term here which will be considered as a source term now, which is the summation of scattering, sigma scattering from group E to group G phi E. And now you will have at this group, this is the group diffusion. You have the leakage at this group from this group. You have the absorption at this group, and you will have the fission at this group, and you have the source, which is all the neutrons that come from other groups other than this group. So in this case, group I not equal to G. And then you will have also the neutron that will scatter out of this. So this will be what? Minus sigma scattering of group G multiplied by phi of group G. So this will give you minus sigma scattering minus sigma absorption. This will give you sigma total. Yes, guys? So I can remove this, and I replace this by what? Sigma total. So this is called what? This is called group diffusion equation. Did you understand now what's the group diffusion equation? We are not going to solve this or do anything about this. I think you will take this in the neutronics class next year if you are interested in taking this neutronics class. So this is the group diffusion equation. So how you will get the group dg? So dg is just d as a function of energy multiplied by the flux as a function of energy in the group G, dE, and now you will average over the energy of the group G multiplied by phi of EdE, and this is the flux in the group G. Okay, guys? Okay? So this is this one. Sigma absorption in the group G will be, or sigma total in the group G will be exactly the same. So this is group G, sigma total as a function of energy multiplied by the flux as a function of energy in the group G, dE divided by the flux in the group G as a function of energy, dE. So it is exactly the same. Now, okay. So if I want to solve this, okay, if you want to solve a diffusion equation, the diffusion equation is a differential equation. This is, let's say, a differential equation. Let's assume we solve it in a one dimension, like x dimension. So this will be what? A linear differential equation with constant coefficient. Why constant? Because all of those will be constant because you average over energy, so this will be constant, let's say. If it is not function of space, it will be a constant coefficient. If it's function of space, it will be with variable coefficient. And you knew how to solve both types of partial or ordinary differential equations. So if we want to solve this, we have to figure out what are the coefficients of the differential equation, whether it is partial or ordinary. So in order to do it, you have to know what's Tj, what's sigma total j, what's the sigma efficient j, and so on. To do it, you have to do this to get the, it's called group average constants. Group average constants. Okay, now if you want to calculate the group average constants, you have to know what? The flux. Okay, I did not yet solve the diffusion equation to get the flux. How I will get the flux? This is the topic of this chapter. So the topic of this chapter is to calculate the neutron spectrum in nuclear reactors. Now, if we are talking about infinite homogeneous reactors, so there is no leakage, and homogeneous, we do not have any heterogeneity. So fuel and moderator are mixed together. Everything is mixed together in a liquid or something like this form. So everything is uniform. So we do not have heterogeneity in this system. So we knew from the last lecture, I just stated this to you, but this is to be proven during this chapter, that we have a chi, then I have 1 over E, then I have a Maxwellian. So this is f of E, which is the distribution function as a function of energy, and this is called chi of E. This is 1 over E, usually goes like 1 over E, and this is a Maxwellian of energy E. This will be to be proven during this chapter. So now let's look how we will prove this. This chapter is fun. If you understand it, it's fun to look for, okay, how the neutron behaves in nuclear systems. And by the way, if you want to look for a complete analysis of this topic, you will find it in Lamarche, Introduction to Nuclear Reactor Theory, or Nuclear Reactor Theory, Duderstadt Nuclear Reactor Analysis, and Henry Nuclear Reactor Analysis. And there is a complete book. It's called, I think, it's called Neutron Thermalization. I think it's by, I don't remember the name of the author, but it is an English author. So it's, I don't remember the name, but it's a compendium. It's a large volume that has all the physical calculation of how the neutrons will slow down, and while they are slowing down, if they will slow down in an infinite system or a finite system, while they slow down, if there is any absorption accompanying the slowing down or not, or when they slow down, there is no absorption taking place or not. So it's called, you will find Lamarche categorize this to 3 chapters. The first chapter is neutron moderation without absorption, and the second one will be neutron moderation. I think it's chapter number 6. Then chapter number 7 is neutron moderation with absorption and fission. Then the last chapter will be neutron thermalization, which once you reach to the thermal energy, you will thermalize with the nuclei of the medium. So this is how Lamarche treated this discipline here. So if we just do a neutron balance, so let's assume that this is the upper energy, and we call this E up. This is the upper energy for the neutrons in the system. And this is 0 here. And then I will have up to 1 electron volt. This is the thermal region. Thermal region. From 1 electron volt and lower. And let's assume I have something like 50 kilo electron volt is here, let's assume. Usually 50, sometimes people will say that 50 is the cutoff for here. And sometimes people call it 100,000. So 100,000, sometimes they call it 50, but let's assume that it's 100,000. And this is 1 electron volt. So let's assume that this is 100 kilo instead of 50. So this is the cutoff for the epithermal is here. Epithermal. And this will be the upper bound here. Then let's assume that this energy is E within delta E. Within delta E. And there is another group here of energy will be E prime within delta E prime. So this one is delta E prime. So we want to do neutron balance at energy E. So neutron balance at energy E. Just to balance the neutrons to this energy. So how to balance the neutrons at delta E? So where the neutrons will be coming to the energy E? Will be coming from down scattering from E prime. Yes? And what else? They will be leaving from what? From, yes, from energy E. And there will be absorption here as a whole like this. So this is absorption. So there is a scattering to this energy, and then there is a scattering from this energy, and there is absorption inside this energy. So if I want to write it like this, I will write it as sigma absorption as a function of energy E at this energy, phi of E dE. This is the total number of absorption per unit what? Per unit volume. Yes? Plus sigma scattering as a function of energy E dE. So what are those? Absorption plus scattering. So whatever you absorbed here, whatever you scatter from this energy. So this is the total losses from energy at energy E. Yes? This is the total. Those two are what? Total loss at the energy E. Then, if we are saying that here between 100 kilo electron volt and E up, we are here. 100 kilo electron volt and E up is here. So we are in what region? We are in the fission region. So there is a source. There is a source in this energy here coming from the fission, which will be what? Sigma fission at the energy E multiplied by what? Phi at energy what? E dE. This is the total number of what? Total number of what? Of fissions. But I have to multiply by what? Nu. This will give me total number of neutrons generated from the fission at energy E. But when I have a fission at energy E, I get a distribution of energies for the neutrons. Yes? If I have a fission, let's say I have the fission cross section is like this. So although energy E is here, I have still fission that take place at energy E. So here is the number of fission that took place at energy E. Each fission produced nu, yes, but those nu, 2.45, they will come with a distribution of energy. So I want to know how many of those neutrons are generated at energy E. So all what I will do is what? This is chi of what? Chi of E. So I will multiply this by what? By chi of E. Yes? This will give me what? This will give me number of neutrons generated at energy E as a result of fissions between E and E plus delta E. Everybody agree? Everybody agree? Okay. Now, this is what's missing now to make the balance. We have the total losses, and we need to get the total sources. So this is one of the sources. What is the other source? Coming from down scattering. So the source for down scattering is just what? Sigma scattering from what energy? E prime to what? To the energy E multiplied by what? Phi of E what? Prime multiplied by what? D prime. But is it this? This is just the one energy that come from energy E between E and delta E prime and delta E prime. But maybe E prime will be here, maybe E prime will be here, maybe E prime will be here, maybe E prime will be whatever. Yes? So I have to integrate. So I will integrate. And when I will integrate over what? 0 to infinity. Yes? But somebody will say, why you are integrating from 0 to infinity? Here is 0. Yes? You have to integrate from, let's assume that this is what? E up. Yes? What's the minimum energy that this can goes to? Alpha what? Alpha E prime. So in principle, I have to integrate from what? Alpha E prime up to the energy E up. Yes? Okay. But if I integrate above E up, there is nothing. So the probability over there is 0 to have anything. Yes? And if I have energy here, and I want to integrate for there is something called upscattering from here to here. The upscattering at the high energy is 0. What does it mean, upscattering? Upscattering means that neutron will collide with another neutron and it will raise its energy. As if you have a billiard ball and there is a slowly moving billiard ball and another billiard ball is fast moving. So the fast moving hits the slowly moving and it gets energy, it gives it energy. This is called upscattering. This does not take place at high energy. This only takes place, and we will see this, take place at the thermal energy. So when the neutron will thermalize with the medium, in this case the neutron energy will be comparable to the moderator energy. And what moderator we are using? Light water. So it is what? Proton, hydrogen, similar mass. So similar to the billiard ball collisions. The energy is similar. So in this case, what will happen? A fast moving billiard ball will knock, which is in this case proton or hydrogen, will knock one of the neutrons, slowly moving neutrons that's drunk, and it will give it energy up and say wake up. So this is the upper what? The upscattering. But upscattering will be just in the thermal energy region. If you are here it's like instead of you are a hydrogen, for example, the hydrogen is what? Is room temperature, 293 or 300 degree. But you have a train, which is the neutron. Do you think that the drunk water molecule or water hydrogen, which is slacky and moving something like about to fall down, and it hits a train, it will give it energy? No. So there is no upscattering in this energy region. The upscattering will be only here. So there is no problem for me if I integrate from 0 up to the upper energy, because the probability that you will have upscattering from this region is what? Is 0 anyway. So you're adding 0. So this is why I said I will integrate from 0 to infinity. Did you understand? Now put everything together, you will have sigma absorption at energy E plus sigma scattering at energy E, all multiplied by the flux at energy EdE, which is, those are what? Losses at what? At E, equal to the sources at E. And what are the sources at E? 0 to infinity, sigma scattering of E prime goes to E multiplied by phi of E prime delta E prime plus chi of E multiplied by 0 to infinity nu sigma fission of E prime phi of E prime. Is it E prime? New sigma fission E prime dE prime, and all of this is dE, and I have to divide here by k, the multiplication factor, to take into account the number, to adjust the number here. So when you do this, if the energy E is around 1 MeV, which is very high energy in reactors, let's say 1 MeV. So the integration between the outscattering from E prime dE phi of E prime dE is less than chi of E divided by k infinity. Why? This is the down scattering term. Okay? If you are at very high energy, here, 1 MeV. 1 MeV is here, maybe because the most probable energy is 1.98. So 1 MeV will be something like here. At this energy, the total number of neutrons generated from the fission, okay, or the fraction of neutrons generated from the fission, is larger than the outscattering from this energy to this energy. You are generating more neutrons at the higher energy than scattering to lower energies. Scattering will be dominant at lower energies here. Okay, guys? So this term is less than this term. So in this case, I can neglect this term. At the very, very high energy, I can neglect this term with respect to this term. And my equation will be what now? Will be just the losses equal to the fission source. Yes, guys? So the losses, which will be sigma absorption plus sigma scattering is what? What's sigma absorption plus sigma scattering? Huh? So this is what? Sigma total of energy E. And this is equal to 0 to infinity sigma fission multiplied by of E prime phi of E prime dE prime nu, okay, multiplied by chi of A. Okay, guys? So this is, to be more precise, this is the number of fission neutrons, number of neutrons generated from fission at this place. So the fission took place at here, but the neutron appear at this energy because of the distribution that you see. So, and this is over K infinity. So now you have sigma total phi of E equal to this. So what will be phi of E? Phi of E is equal to what? K of E divided by K infinity divided by sigma total of E multiplied by nu, and this is what? Sigma fission of E prime phi of E prime dE prime from 0 to infinity. What's this? This is the total fission per fission rate per centimeter cube. So it's a constant. It's a number. So this is what? Constant. Yes? A constant. And what's this? Another constant. And what's this? Another constant. So in this case, my flux near the 1 MeV will be just what? Phi of E multiplied by a constant divided by what? Sigma what? Sigma total as a function of E. I just draw the plot for sigma fission, and we know that it was like this, and something like constant at the high energy. Yes? So sigma total at high energy nearly is a constant. So if sigma total is constant, as a function of energy is constant, so this means that the flux as a function of energy is proportional to what? What? Chi P. And this is the plot I just plotted for you a couple of minutes at the early beginning of the class. Yes? I showed you the distribution function as a function of energy is chi distribution at high energy. Okay? So, yes?
In this class, we're going to consider 100 keV high energy, or earlier you said 50 keV.
Put it 100. This guy, he put it 50, but usually the acronym, they put it from 1 electron volt to 100 kilo electron volt is the cutoff. But put it 100. It depends on the author, but usually I saw lots of authors who put 100 kilo electron volt as the cutoff for the epithermal. Okay, guys? Yes?
Can you explain why that integral is a constant again?
You integrate over energy, Ibrahim. So if you have f of x, let's say sigma of energy is something like, let's assume like it's exponential e to the power of minus e prime. Okay, and the flux of energy is Maxwellian, so it will be e to the power of minus e prime dE prime from 0 to infinity. So this is what? E to the power of minus 2 e prime. Yes? What's e to the power of the integration of e to the power of minus e prime? 2 e prime. So it will be what? 1 over 2 minus e to the power of minus 2 e prime from 0 to infinity. E to the power of infinity is 0, and e to the power of 0 is 1, so it will give you 1/2. So it's just you integrate over a definite integral. So you have upper limit and lower limit, so you will substitute whatever function you get at the upper and whatever function you get at the lower, and it will give you a constant. Okay, guys? So now we knew that our flux at the energy 1 MeV is almost what? Constant. But this is based on what? Based on the assumption that my outscattering term at high energy is what? Is less than the fission source. Yes, my out scattering from this energy here, which is very high at 1 MeV, is less important than my fission source at this energy. And this is true at very high energy. At very high energy, whatever you produce from fission is more than what you lose through scattering. But if this is not true, so I have to do what? I have to play with this formula. Yes, guys? If this is not true, I have to play with what formula? If we are not at 1 MeV, I have to do what? I have to play with this formula. So to play with this formula, this will give you sigma total as a function of E, phi of E, dE, and then equal to 0 to infinity, sigma scattering of E prime goes to E, phi of E prime dE prime, which is this part here, plus the chi of E divided by K infinity multiplied by this new sigma fission of E prime, phi of E prime dE prime, then you have dE here. So if this is not true, all what I want to do now is to do what? Is to do iteration. So I will say, I will guess a flux at the first initial value. And let's guess the flux at the very initial value to be what? To be in this form. Then what will happen? So you take this flux as what? Chi of what? Chi of E divided by what? Sigma total. But you evaluate this flux at E prime, and there is a constant here. Yes, guys? So when you do this, this will be just chi of E divided by what? By sigma total of E dE prime. Huh?
Do we drop that constant, or is there?
Nu, the constant is here. So again, what's this? A number. So it's what? It's a constant, and this is a constant, this is a constant. So I can remove everything here, and I will write it as what?
Some constant times chi.
Some constant times chi. And I can come here and also substitute with the same flux, which will be what? Chi of E prime multiplied by a constant C divided by K infinity, so some constant C double hash or something like this, divided by sigma total. Okay, guys? So to get the flux, 5E will be just 1 over sigma total of E, okay? Delta E will go as delta E from here, and delta E will go from here. Then the flux will be just this divided by sigma total. So if you took chi of E as a common factor, you will end up with what? You will end up with 1 over chi of E, the integration from 0 to infinity, sigma scattering of E prime goes to E multiplied by chi of E prime, delta E prime divided by sigma total as a function of E, plus what? Plus 1, because I will take the constant outside and there is another constant, so there is a constant multiplied by everything here. Okay guys? So what's this? Chi of E over sigma total of E. I just defined it over there, and I told you this is the initial guess for the flux. Yes? So the flux of energy E will be just the initial guess of the flux. I call it naught here, multiplied by 1 plus 1 over chi of E multiplied by this integration. Okay, and this is how you will do it. So you will do, okay, you will get the second value, okay, substitute in the first value and so on until you reach to a steady state value for the flux. Okay guys? Okay guys? This is if you are not near the 1 million electron volt region. But typically, if you are 0.5 MeV and above, it's safe to assume that your flux as a function of energy is just proportional to chi of E divided by sigma total of E. This is a good approximation. This is to a very good approximation for the flux. If you are above half MeV, the flux is proportional to chi of E divided by sigma total of E. Then next lecture, what we will do is we will try to see now, this is the shape of the flux. So now, this is the flux. This is the flux as a function of energy in the reactor. So now what we did is we got the shape of the flux in the fast energy region. So this is what? Chi of E. So this is the fast energy region. We were able, by just doing neutron balance on the energy bins inside this region, to figure out that, okay, if I am above half a MeV, which is 500 kilo electron volt, 500,000 kilo electron volt, the flux to a good approximation, to a very good approximation, can be taken as proportional to chi of E divided by sigma total of E. So this is the first thing. The next step is to go and try to study the neutron moderation now below the 0.5 MeV, or let's say below the 100 kilo electron volt. How the neutron will behave in this energy region, and we will figure out the next time that it is what? 1 over chi over E. Then we will discover that it is in the thermal energy region. It's what? It's a Maxwellian. So I give it to you for granted from lecture number 1 that this is the shape of the flux inside the reactor. this is the derivation now of, and I remember in the first lecture I told you in chapter number 4 or 5, we will figure out how to calculate or how to show that this is the neutron distribution inside the nuclear air. So now, this lecture, we showed that to a good approximation in the fission energy region, the flux is proportional to chi of A divided by sigma total of A. Okay? Next lecture, we'll try to study the epithermal region, and this region usually is the region where you have the moderation for the neutrons. The neutron energy decreases until it reaches to the cutoff for the thermal energy region, the one electron volt. And in the 1 electron volt, there will be a different treatment to show that the neutron distribution is just Maxwellian. Okay, guys? So I will stop here. Next time, we will go in the slowing down region. Any question? Okay.